Hello student, I am Om Prakash Dubey, chemistry faculty. In this class I am going to discuss about the dissociation of polyprotic acid, or we can say polybasic acid. Polyprotic acid or polybasic acids are the acids which gives more than one H plus ion to the water. Like as for example, many examples are there like H2S, H2SO4, S3PO4, phosphoric acid, orthophosphoric acid, H2SO3. Many examples are there of the polybasic acid and the polyprotic acid. Polybasic acid or polyprotic acid dissociate in a successive steps, one by one gives 1 by 1 H positive ion. Like as for example, if H2S is taken, H2S is a dibasic acid, it gives 2 H positive ion to the aqueous solution to the water. Now in the first step, the H2S, when H2S gas dissolved in water, it gives H plus ion to the water and forms HS minus anion, and the dissociation constant of this equilibria is 1.1 multiplied 10 raised to the power minus 7. In the second step, HS minus, again it gives 1 H positive ion and forms sulfide ion, H2 minus ion, and the second equilibria constant, second dissociation constant is 1.0 multiplied 10 raised to the power minus 14. For a polybasic acid or polyprotic acid, the first dissociation constant is much larger, much greater as compared to the second dissociation constant. If a tribasic acid is dissolved in water, the first dissociation constant is much larger than the second dissociation constant. The second dissociation constant is much larger than the third dissociation constant. What are the reason of this variation? The first dissociation constant is way much greater as compared to the second dissociation constant. See, in the first step, H2S, the dibasic acid, it gives H plus ion, it gives proton and forms the anion. In the second step, the anion forms doubly charged anion, the singly charged anion forms the doubly charged anion by losing proton. Since singly charged anion forms the doubly charged anion, it requires lot of energy, much more energy to form the doubly charged anion from the singly charged anion. That's why it occurs less readily as compared to the first step, the dissociation of the H2S into H positive and HS minus. That's why the first dissociation constant is much larger as compared to the second dissociation constant. Since the first dissociation constant is much greater as compared to the first dissociation constant, that's why the concentration of the cation and anions produced in the first step is much greater as compared to the second step. That's why the calculation of H plus ion, which is produced in first step as well as in the second step, but the concentration of H plus ion in the first step is much greater as compared to the second step. That's why here we can calculate the H plus ion from the first step, not from the second step, because the concentration of H plus ion in the first step, it is much greater as compared to the second step. Therefore, the calculation of H plus ion, the concentration of anion HS minus and the concentration of pH of this solution can be only done by the first dissociation step or first equilibria step. In this class, I am going to discuss the problem based on the common ion effect or on the polyprotic acid or polybasic acid. Calculation of ions present in the aqueous solution of a polybasic acid or polyprotic acid. Like our question is, the concentration of H2S in a saturated solution of the gas in water at 25 degrees C is 0.1 m. The concentration of H2S in water is 0.1 m. Calculate the concentration of the H positive, the HS minus and the H2 minus ions in a saturated solution of H2S. We have to calculate the H plus ion concentration, the HS minus ion concentration and the H2 minus, that is sulfide ion concentration in the aqueous solution of 0.1 m H2S. The first dissociation constant and the second dissociation constant both are the given. First dissociation constant 1.1 multiply 10 raised to the power minus 7, and the second dissociation constant is 1.0 multiply 10 to the power minus 14. First of all, if we have to calculate the H plus ion and the Hs minus ion concentration and H2 minus ion concentration, we have to write both the dissociation equilibria. The first dissociation of the H2S, it gives H plus ion and the Hs minus ion, and in the second step, Hs minus ion, it gives H plus ion and the sulfide ion in the aqueous solution. If we have to calculate the H plus ion and the Hs minus ion concentration in the aqueous solution, we have to consider the first dissociation equilibria. And in the first dissociation equilibria, the concentration of the H2S at the equilibrium is C1 minus alpha, the H plus ion concentration is the C alpha, and the Hs minus is C alpha. From first dissociation equilibria, we can write the dissociation constant expression, which is H plus ion Hs minus upon the concentration of H2S. And see, in the first dissociation equilibria, the concentration of H plus ion and the Hs minus ion are equal. The first dissociation constant is very large as compared to the second dissociation constant. That's why we can neglect the H plus ion produced in the second step or the second dissociation. Now the H plus ion and the Hs minus ion concentration are the equal. So we can also write H plus ion concentration raised to the power 2 upon the H2S concentration, and the H2S concentration is given in the question, which is 0.1 m. Now the H plus ion concentration can also be written as under root K multiply the H2S concentration, since the alpha, the degree of dissociation of this weak acid, this H2S, is very small as compared to that of 1. That's why we neglect the alpha as compared to 1. Now the H plus ion concentration, K value is given 1.1 multiply 10 to the power minus 7, and the H2S concentration is given, which is equal to the 10 to the power minus 1, the initial concentration, because the dissociation is very less. Now the H plus ion concentration, it comes 1.0 multiply 10 to the power minus 4 moles per liter, and the Hs minus is also equal to the H plus ion concentration, which is 1.0 multiply 10 to the power minus 4 moles per liter. And H plus ion and Hs minus, both the concentrations are equal. Now if we have to calculate the sulfide ion concentration, we have to consider the second dissociation equilibria, and from second dissociation equilibria we can write the dissociation constant expression K2, which is H plus ion concentration H2 minus ion concentration upon the Hs minus concentration. Since the H plus ion concentration in this solution is much more in the first step as compared to that of the second step, the total H plus ion concentration, we can also say the total H plus ion concentration in this solution is equal to the C alpha, because H plus ion concentration produced in the second step is very less as compared to the first step. The H plus ion concentration and Hs minus ion concentration, since they are equal, that's why the dissociation constant, the second dissociation constant, is equal to the H2 minus ion concentration. The H2 minus ion concentration, which is equal to the second dissociation constant, since H plus ion and Hs minus ion concentrations are equal. Now the H2 minus ion concentration, which is equal to 1.0 multiply 10 raised to the power minus 14 moles per liter. Now in general, in case of the dibasic acid, if dibasic acid present alone in the aqueous solution, then always the concentration of doubly negatively charged anion is always equal to the second dissociation constant. In this class, I am going to discuss about the relative strength of acids and bases. The relative strength of acid is the ratio of strength of acid 1 and the ratio of strength of base. Ratio of strength of acid and the strength of base is called the relative strength of the acid, and the strength of acid is known by the H plus ion furnished by any acids or OH minus furnished by any base in the aqueous solution. Now we can write the relative strength of acid is equal to the strength of acid 1 divided by the strength of acid 2. Simply it is the ratio of strength of acid 1 and the acid 2. And similarly, the relative strength of base is the strength of base 1 and the strength of the base 2. The strength of the acid 1 is known by the H plus ion furnished by the acid, and let us take an example of the two acids like Ha1 and Ha2, which dissociates in the aqueous solution. Ha1 in aqueous solution it dissociated as H positive and A1 minus, and Ha2 it dissociated as H positive and A2 minus. If the concentration of both the acids are equal, if the concentration of both the acids are equal like C, and the initial concentration of the H plus ion and the anion is 0, 0. If the degree of dissociation of this weak acid Ha1 is alpha, then it dissociated C alpha 1. The degree of dissociation, it may be different or it may be equal. If it dissociated C alpha 1, then the H plus ion formed in this solution is C alpha 1 and C alpha 1. The concentration at the equilibrium is C1 minus alpha 1 and C alpha 1, C alpha 1. Now we can also write K1 for this acid. The dissociation constant of this weak acid is C alpha 1 multiply C alpha 1 upon C1 minus alpha 1, and the K1 is equal to C alpha 1 square. Since it is a very weak acid, the degree of dissociation can be neglected as compared to 1. Similarly, if the degree of dissociation of this acid is alpha 2, it dissociated C alpha 2, it gives C alpha 2, it forms C alpha 2, and the at equilibrium C1 minus alpha 2, C alpha 2 and C alpha 2. The dissociation constant of this acid can be written as C alpha 2 square, C alpha 2 square, and alpha 1 for this weak acid can be written as under root K1 upon C, and alpha 2 for this weak acid can be written as K2 upon C. The ratio of degree of dissociation is the relative strength of the acids 1 and the acids 2. Now we can write the relative strength is the ratio of degree of dissociations. Now it is equal to the under root K1 upon C, K2 upon C. If the concentrations are different, then we can also write C1 and C2 here. If the concentrations are equal, the relative strength of the two acids are the ratio of dissociation constant under root the ratio of dissociation constant is the relative strength of the acids. And similarly, we can also determine the relative strength of the bases. The relative strength of the bases is the ratio of under root Kb1 upon the Kb2, the dissociation constant of base 1 and the base 2. Thank you.